Okay, so let's try to catch up a bit where we left things. We will pretend that nothing happened in the last 15 minutes of the previous class because it was a total mess. And we'll see the same thing just with the normal pace without haste. Before we go there, let's see what was left here as pink, which means homework. We defined this plus type, which for some reason seems more mysterious than multiplication or the arrow type. And we have seen how to introduce elements of this type. In other words, we have seen the constructors of this type, which is the in left or the in right or the lefting or the righting, the rightment, I don't know. We call them how you like them, how you prefer. And okay, so the question here was what's missing? And they are like, okay, can someone answer this? Like here? Yes? The elimination, obviously the elimination rule, first of all, and then probably some other things, and the equations, right? Vita and eta. Okay, so the elimination rule, it's kind of not so trivial to write down in the proper way, but we can cheat. And I will show you a kind of easier way to write it because you already know what functions are. So the little problem would be if we didn't know what functions were and we want to define this. It's not a really big deal. We'll see what's going on. But okay, so let's see what the situation is. Always I want to say how to use something of this type. And the idea is that this should be able to produce some kind of element in some kind of type. And in order to take advantage of this thing here, which remember it can be either an in left together with a little a or an in right together with a little b, it means that I will be able to use this if I have ways to use this a and use this b. So the idea here will be like, pretend that you have a function that goes from alpha to some type delta, I don't know, and you also have some function g that goes from vita to the same delta, to the same type delta. And the idea is that if you have all these, you should be able to produce something of the type delta. Because here, there is hidden something that is of type, a little a that will be of type alpha or some little b of type vita. And I have ways, in either case, I have ways to produce something of the type delta. So I already know this part, which is not always so trivial to figure out. So I will produce something of type delta. And now, just to get you used to some kind of like abstract notation that might not make a lot of sense if you see it suddenly, so I would like to do it gradually. The whole point here is that I should be able to include all this information in my notation. The notation I will use will be this. It will be kind of convoluted, and if you haven't seen it in some programming language, it might seem very weird, but let's try, give it a try. Try to match W with all possible cases, which I will list here. So it's either a lefting of some little a or some x, I don't know, or the right end of some v. And in each case, I will have to tell you what to do. In this case, you will call f with the argument a, and in this case, you will call g with the argument b. And don't think of this like 3 lines, think of this like just one thing, like a very weird integral thing that you understand like an atomic thing. So this whole thing, I don't want to use parentheses, but I will. Yeah. So this whole thing will be of type delta. Any questions? It's huge. Another useful, not useful, sorry, common, most languages either use this, match this thing with those cases, or case W of, it's just an alternative name, depending what your favorite language is. You have seen one or the other, or none of them, and in this case, you should change your favorite language. So let's see what's going on now. as Raphael said, right? Yes, as Raphael said, we also need some computation rules, vita and eta, and let's start with the vita thing. But before I go there, notice that there is too much bureaucracy here. Essentially, what's going on is that I only need to tell you these two functions, and you should be able to know what to do with them. Because I'm simply copy-pasting this A here and this B here. So another way to see this is, instead of producing an element of the type delta, to produce a function from alpha plus beta to delta. I'm trying to find a different color. Okay. Alpha plus beta to delta. And we could call this function in a much prettier way, like something indicative, like it's a choice between f and g. Or, I don't know, f bar g. So how does this function work? The idea is that you give it something of this element, and in case it was a lefty, then it will call f and will produce delta. In case it was a righty, it will call g and will produce a delta. Okay, it's kind of way easier to write this thing like we are saving a bit of the planet with this, but let's try to state the equations with either way, either this or this. Ideas for like a beta computation rule. We want to know how this thing will progress. So if you have this, and you apply it to something, if you think of this as a function, you should say what this thing does when it gets applied to some random element, some arbitrary element of this thing. I will call it S because it reminds me of sum. And a good question is like, how many equations do we need? Because if I try to say how this will compute, I'm helpless here because I don't know what the form of S is. So I will look into it and I'll say, okay, in case it was like an in left A, then this should be equal to something. And in case this was like an in right B, this should be equal to something. And now I think I can get someone to help me here. Yes?
F of A and GB.
F of A and GB. Yes, exactly. So this is how this thing computes. Okay, you plug something, it looks in this argument. If it's in A, it will call F, and the whole thing will get substituted by this much simpler thing. Okay, makes sense? How about the eta rule? This is kind of more. Remember what eta, how eta usually look like. When you get something, and you kind of complicate it, and you end up back to the same thing you started. Arati?
Ίσως να βάλουμε το σύμβολο που λέει με τις αγγείλες F κάθετος G και αντί για F να βάλουμε FA και αντί για G.
You're approaching this until the last thing you were going on the right track. So you are suggesting to put here FA and GB, right?
Yeah.
And this would be equal to what in this sense?
EFA, όχι, in
Needs to be S, no? The element.
Okay. I think what would you put here?
in L πάλι το ίδιο αλλά με in και δίπλα το δεξί.
No, here, the fact that you're using F and G here is kind of problematic. You want to use in these parts something that you will already know the answer. Like, okay, what will happen if F happens to be in left? Most of the etas we have seen look like useless, look like things nobody would write. But what would happen if F was in left here and if G was in right here? and I call this on some W. Like if let's match W, and in case it's a left A, do in left of A. In case it's a right B, do in right of B. What's that whole thing?
It's like a tuple, no?
It's like a? It's not a tuple. Because in the end, I will either call an in left or in right. We are lost. Are we lost? A bit. Okay, so I think I will write it carefully here. Okay, case W of I found a lefty thing, and in this case I will just. Okay, sorry, I'm mixing notation here. Maybe this is why I'm confused. I'm using both notation at the same time. This is terrible. I'm using this left blah blah and the sin left. It's the same thing. Okay, sorry, it's a different like alternative notation. I will try to use it properly here. No, because this way it will look really bad. Okay, how can I make this better? It's very convenient to actually change the notation. In case you find the lefty, okay, so let's see like that. If I call in left, in right, on some S, or some W, I don't know, what will this be? Yes?
Yes.
Yes, that's what makes sense. Or it's only one person following me right now. No?
That's what I said in
Okay, was it? Okay, sorry. I apologize. It's recorded. We'll find out. Okay, sorry. Sorry we spent this time here. So this is the eta rule, one of the ways to write the eta rule. And I'm saying we are kind of cheating here because the whole development of plus depends on the fact that you already have an arrow. And maybe I don't even want arrows. I do, but maybe I don't even want arrows. So there should be a way to write this down without depending on this type. I don't want interdependencies between the things I'm developing. These things I consider quite primitive. And we'll see that the trick is that we have to remember that all these rules here have like usually invisible stuff that I never bother to write down unless something interesting changing there. So here I can have some context gamma, but nothing interesting happened here, so I didn't bother to write all those things. But as we saw in the function, in the arrow type, let's remember how we introduced the arrow type. It was something like if you have an x of type alpha, and from this you can define something like b of some type, I don't know, beta. The idea is that out of this I can get, without this dependence anymore, I can get a lambda xb, and this is of type alpha cross beta. This was, I think, the first rule that we met where I had to use this notation. I had to make it explicit because something changed here. Otherwise, we don't bother with it because we consider that, okay, you can use all those things in arbitrary contexts when you have arbitrary contexts, okay? So something similar could happen here. If I didn't have this, I should write something like that. I will change it on the fly here. Something like if A is of type alpha, and from this I can get some kind of D, I don't know, dA, of type delta, and similarly here, and I would have to change my notation here a bit. For the time being, I want to stick with the functions because we know functions, and when we get a bit more used with the context, this will be kind of trivial to see how it goes. Okay, questions? So we know what the plus thingies are, and we know how to compute with them, and we have concluded pretty much the basic, let's say, types, but there are some very important things missing, and for these important things, we need to talk about what are called families of types or dependent types. And we'll do this slowly this time so that we don't end up in a mess. It's kind of a synonym. It's not a different thing to say family of type or dependent type. The examples here is like when you say consider some space, Euclidean space, I don't know, R in the power of n, and you want to say like that this is already a space, a Euclidean space, I don't know what it is, but this depends on an n, it has a parameter. It's not the case when you say something, okay, I will work with the reals, the plane, right? This is already a type. This is space, a type, call it how you like. This is not really a type unless I have an n lying around. Without this, where did this n came from? Or, I don't know, when you study something like, in analysis, you see like the continuous functions maybe, or something like that, defined in the closed interval 0, 1. This is already a type, this is a space, okay? There's no dependency here. But the moment I say, okay, consider this, now this thing depends on two things, okay? It's a dependent type. And I cannot have this by itself. I need to say that I have a context. In this case, I have A, which is probably, I don't know, let's say it's a real number, and B, it's a real number. So this is a family of types, because for each choice of A and B here, I can consider this a different type. And this is a family of types, because for each natural number n, let's write it properly, I have a new space, okay? Does that make sense? Is that it happens all the time in mathematics. We don't notice it, probably, but it's there. It's pretty much everywhere. So I want to draw a picture that will be very useful to have in mind. First of all, I could write something like this. Like I have an I in E. I'm using the letter E to remind me of the word index, but it's just indicative. There's no further meaning to it. And I have here something like D, which is a type. So if I write this down, it means that in D, it's possible that some E's may occur here. E may occur here. And so if I have this, I can say I have a dependent type or a family of types indexed by E. It's the same thing, they're synonyms. Okay. And I could, of course, move this the other way around and pretty much maybe call this like that. Might be easier on the eye if you are used to this from somewhere. To say that D is a family of types indexed by E. It's like a function. You give it an E and it tells you what type it is. It's a different type. Or could be the same, but in theory it can be different. It can depend on this I. Okay, so the picture I want to draw, which is very essential, and we will build on this picture, is first I will draw this I here as a kind of vertical thingy, and I will use its elements. This dot here are its elements. I don't know how many elements it has. It could be an infinite number, 0, 1, or more, it doesn't matter. Let's say this is like I0, I1, I2, and so on and so forth. The idea is that on each of them, I will associate a new type. So think of a type floating over it, like that. And it's not necessarily the same type, but it's a type. It could be the same, but it's not necessary. Maybe, for example, the second one looks like the Booleans. Maybe this is the Booleans, as an example. I don't know, maybe these are the natural numbers. I don't know. And the idea is then that, okay, this is the type D of I0. This is the type D of I1. This is the type D of I2, and so on and so forth. And we have more types here. Does this picture make sense? Think of this like, you can think of this like something moving in time, maybe. Usually this could be like seconds in time. And like on the first instance, the type is this, and then it changes, and changes. Okay. So the whole thing I drew here is just a drawing of this situation. right? This thing, I just drew it out. And now, the same way we were in the binary cases of products and sums, we said, look, as soon as you have this, what was this? Two types. You can form their product. And as soon as you have two types, you can form their sum. So, right? And I want to do the same thing and say the following. As soon as you have this situation, you can form a generalized product. And as soon as you have this situation, you can form a generalized sum. And this situation will not change. And this should also make sense because even in the binary cases, the situations did not change, the givens, the context. I had two types, I can make the product of them. I had two types, I can also make the sum of them. And I will do the same thing now that I have a family of types. I have I many types. I can say it like that. I don't have two, I have I many types, one for each I. Make sense? Okay, so I will draw the elements of each of this type to give you a motivation. I'm not sure if it's easier to say first the product and then the sum or the other way around. I will do the product first because we started with the product in the binary case. So every color I will use now will be one element. Other people who cannot differentiate colors here? No, right? It has happened before? No. Perfect, okay. So let's draw one element of this space. First of all, let me put some more balloons here. Maybe one only has a single guy here. Maybe this thing is like the real numbers, I don't know. Okay, so I will start with, purple, okay. I will draw one element of the product type. It's this. This would be very annoying, I think. Yeah. Okay. You can think of it like something like that. Oops, no. I skipped one. Something like that, okay? If you've seen this in set theory, something similar in set theory, it looks like a choice function. Like for each I, it will select a specific member that will be there, with the difference that these are not sets, and there is some sort of, I don't want to say continuity involved, but there's some kind of space between them. I will draw one more, just to get the idea. Maybe here is the same. I don't have the obligation to avoid something I have already picked. And as a matter of fact, here I don't even have a choice because there's only one. Okay, so this is a second element of this type. Okay? So, conclusion, the elements of, so what is the name of this type? The name of this type is the product type. I'm defining it right now. So, I will need this. As soon as you have this, you can form this new type, which is called the product type. And we denote it like that. There are actually various notations. I will show you three of them. Like this. And, I forgot to say something. Sometimes we use this of I here to emphasize this, but it's not necessary. Okay, so this thing is a type. So I could write here, whether I write or not, it's just psychological. I could write it like that, okay? So it's the product of all these types. That's how it's called. And we will find out, starting from next week, we will meet category theory. how to defend these names. You could call it something else temporarily, but okay, we will call it a product. A different, okay, so how can I visualize the elements of the product? They look like functions from this, from I to all this mess here, which is not really a mess, it's kind of tidy, so that they associate, for example, I2, the orange element will associate I2 with this guy, and will associate, I don't know, I1 with this guy, and so on and so forth. So the purple thing, these arrows here, I can consider that this is one element of the product type. So they are functions. So it's a very convenient notation, I think much more intuitive, to say, to write the type like that. It takes an I, a little I of type big I, to some element of D of I. So D of I will change. Here, the second was the booleans, the third was like weekdays, or I don't know, and this was the real numbers, and so on and so forth, okay? So these are the elements of the type. How I use them? Exactly like functions. So I will not even bother to do that. We'll write it down later on. I don't want to do it now. And how do we create them? Exactly like functions. I mean, we use the same lambda, so they are functions, okay? Essentially, you might ask yourselves like, and what about the functions we already have? Like these things that we know as functions. The same thing is a subset, it's what's going on with that. And we'll get back to it right in a few minutes. If this is clear, I want to move on to kind of the same picture, but show you the sum. Is it okay? Okay. And I already regretted the fact that I did not copy paste it when it was the correct time to do that. But okay, let's try to do this and maybe remove the clutter. Okay, so I just want to remove what's colorful, and I think it's faster to do it like that. Okay. Okay, some points got swollen. I will bring them back. Okay. Okay, so am I ready? Yes, I'm ready. What is an element of this type? Here is an element of this type. It's gone. Not exactly this, together with its shadow. So this pair, this thing, this element, why do I need the shadow? Because maybe, like, this is the natural numbers as well, and this is the natural numbers as well, and then the natural number 2 of this thing is a different inhabitant of this big type than the natural number 2 of that thing. So it's not only, so this is not only the information I want. I want together with the shadow, the projection of this, okay? So this is one element. Let's write one more element like this, together with the shadow. And I don't know, third element, maybe like this thing, together with a shadow. So I am showing 3 elements of this space here, of the sum, and I'm showing like 2 elements here. Maybe I could write one more, just like quickly, something like that. Does that make sense? So elements of the product types are functions that behave very tidily. They don't throw these things. I mean, if you see that theoretically, set theoretically, probably you would be tempted to unite all those things and then say it's a function from here to this mess, and such that it's being careful so that it respects these things, right? But here there's no mess. These things are tidy. These things are separate, different types, and these functions take care of that. Like the output of them belongs to the correct type depending on what the input was. Is it okay for products and sums? Okay, similar thing. I will just change the P of this. And obviously I will want to change to have a different notation as well for sums, just like I had for products. And for products, in order to come up with this notation, I ask myself, what, in the end of things, what are the elements of this type? They are functions, so I will use something that reminds me of a function. In the end of things, like, what are the elements? How can you visualize elements of this type? Anyone has an idea?
It's like everything in one box, no?
I'm looking at an answer that it's like something we have already met. Because here we figured out I can visualize these things like functions. And we know functions, so we say, I will use this notation, which I know because they look like functions, and I'm looking for something similar, like the orange element here looks like a function. The orange element here, what does it look like? Arati? It's a pair, yes, it's a pair. A pair of what things? Yes, we'll just put them the other way around. We'll say first the index and then the other thing, because the second thing depends on the first, right? Okay, so it's like, they're like pairs. So it makes sense to denote them like that. To denote not the pairs, sorry, to denote the type of them like that. It's a Cartesian product of some little I of type I, and the second component is of what type? It's of D of I, right? It can change. And similarly, how do I use them? The same way I use products, because I have the two projections. Like, I can project from this thing, from the orange thing, I can project the first projection, and this will be equal to which I? Exactly, I1. And I can project the second projection, and sorry for the indices if you don't like them. It could be 0 and 1, this is confusing. And in this case, it will be what? And I is an element of I1 is an element of I, and this thing will be, let's say this was, I don't know, false, and this was true. So this will be like false, and this is an element of D of what? Yes? I1, and like, how could I describe it? It's correct. What you're saying is correct. It's like D of the P1 of orange, which happens to be I1. Okay? Good. I think we have an intuition of these things. And I already told you that we cannot justify the names completely because we don't have the vocabulary of category theory yet. We will have it starting next week. But we can justify somewhat because we have an idea of arithmetic and sum and product. And at the very least, we should verify what's the relation between this product and the binary product and this product and this sum and the binary sum. Okay, so the binary things should be special cases of these things, and I want someone to figure out how I can do that. Do we get what the challenge is? Essentially, I want to get rid of the binary things as primitives and say, give me P and sigma, and binary products and binary sums are like special cases of these things. But I have to be careful of what these things are. 1, 2, Manolis.
Okay, so if we want the binary product of A and B, for example.
Let's do product first, okay?
We can just have an I of cardinality 2, and D of by 1 is A, D by 2 is B.
Okay, so first of all, we have to say what the dependent type is. And Manolis here likes an element of two, a type of two elements.
We could have a Boolean, for example.
We could use the Boolean, so like 2, which would be like there was a question, a homework question. I think everybody ignored this one because in the arithmetic there was something like this. can we say something about this, where alpha and beta are types? We learned this in high school, alpha plus, I think, alpha plus beta to the squared. This should be something, and you are tempted to write it, and it would be nice if you write this. How you want to write it, plus beta. Did I make a mistake? Of course. I need to go back to school. So if you want to defend this, like, the first thing you want to answer is like, what is this mysterious 2? And Malo says, okay, pick the booleans. It is one way to do that because the booleans have 2 elements. But I think if we do that, we are abusing booleans. Like, booleans were created for a different reason, right? And we could say, okay, I could either create a type which only has 2 new things for the sole purpose of having 2 things, or I could maybe use 1 plus 1 if I have the plus and the unit. But now, of course, if your objective would be to replace sum, and you tell me the binary sum, you will have a problem here because you are using sum here. But you could say, okay, let me just create a binary type with 2 elements, and I will use this to get the binary sum. Okay, so the picture here then is like this. So let's say the 2 elements are called, I don't know, not star, but square and heart, whatever. So this is my index. And here I have which type? Manolis, help me. Alpha, yeah, okay. Eventually, I will swap the Greek alphabet to big Latin letters. The distinction in the beginning is because I'm using the big ones for like set theoretic comparisons. So this, let's say this is A and this is B. And now if you form what were we doing? The product. If you form the product, what are its elements? They are all possible choice functions that you have here. So like one element of this thing has to make a choice where to send this guy and where to send that guy. And if it says sends this guy to A and this guy to little a and this guy to little b, this will correspond to the idea that you are forming this product. Okay? So instead of doing in left on your tuple, you will do something like, you will apply which function? Help me here. You will apply this W to the square. And it will say, this is A. If you apply the W to the heart, it will say this is B. So actually, the other notation is closer to this, so we'll use this. You are getting the left projection, the right projection. Here you are getting the square projection or the heart projection. Make sense? Okay. So we have justified that products are a binary, a special case for, binary products. I can get them as a special case of P types, right? Just use as an index something that has 2 sets. And obviously we want to do the same thing with sums and find out that I can get a sum type, a binary sum, as a special case of a generalized sum if I just use something that has 2 elements in the index. Make sense for everybody? Yes? Okay. Another special case that's very nice to consider is like, first of all, where are the arrows? Because I said earlier, this was kind of a spoiler, I shouldn't have said it, that eventually we will get rid of these things, and these things, we can't get rid of these things, and these things will be more primitive. Okay, so we get this as a special case of that, we get this as a special case of that. How do we get this? I will give you like 1 minute to think of this. It's a special case worth considering. One special case like fix the index to be not some random I, 2 things.
The index is A here, no?
The index is?
Should be A.
You're getting somewhere? Okay. And what is the family?
And then it's like element things of B, so I do not know how to express it.
You give the half of the idea here. So A will end up being the index set, but like what is the family? Because okay, let's put A here.
And it should be B at each point, no?
It should be, yeah, what?
B at each point.
At this point, exactly. So this is the special case where it's a vacuously dependent type because it doesn't really depend, because in each point in time, it's always the same type. B, 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 right? So here our copies, all of them are B. Right? Okay, so what is the dependent product of this thing? They are functions that take each of these things to that, but these are all B's, so I can implement, this is the correct way to say, this type if you give me P. And notice that in this case, I don't even need to have an access to an extra primitive 2-element type or a special thing. As soon as I have this thing, it's like saying, okay, I will, if B of A is equal to B for all A's, I end up in this special case. So going left was like the binary specialization, which means that this thing is ugly, which means that I want to move it here. And this is not just OCD, this is more than that. So the things on the left mean specialize in the case you only have two things. Your family only has two things. Going on the right, downwards right, means consider what happens if all the balloons are the same type. And we didn't do that for sigma. So what happens if sigma, in the case of sigma, consider this thing again, this picture, I don't need to draw it again. And now the question is, like, what is the sum here? Remember, the sum is a pair of things, something of this, together with an element of B. So what happens here? Can somebody see that? Let's see, let's play around. This is A, right? Okay, I will take like A2 together with this thing. In essence, the element of the sum type was A2 together with this B here, which was an element of B of A2, but B of A2 doesn't really vary, it's just B. Manolis? You get the Cartesian product again, and this should not be so surprising, the fact that you can define multiplication from addition in the sense that in school it was not as surprising as Manolis was not as surprised in school. Like, multiplication is just repeated addition, and pretty much this is what's going on here. Like, you have A many B's. This is literally multiplication, okay? You have B plus B plus B how many times? 8 times. So you get A. This is one way to reach A times B. Is that okay? I hope you're following me. Questions? Okay. Yes, Manolis.
Now it's kind of weird that we can get the Cartesian product in two ways and the other thing is just once, is it not? Maybe not.
It is a kind of OCD, and in general, OCDs are quite insightful. This is good. I personally don't find that weird. I mean, in this sense, you are getting repeated addition, repeated multiplication, and you're walking this way. I mean, there are two generalizations you can do, and this ends up having two forms. Okay, maybe you would like to have like that. That's what you mean? Something like this?
Not really, I don't think so. I don't know, maybe.
Okay.
Maybe we could get, like, again, maybe I'm overthinking this, but we could also get the sum by, like, a sum of ones or something, like, the further analogies to how we define, like, addition is lots of successions, one after another, basically.
Here, you mean? Like sum of a bunch of ones?
Yes.
This if you sum a bunch of ones, essentially you will get just like a type with that many elements. I don't think you can get the A plus B. But anyway, let's call it a break because it's about time for a break. It's a good time for a break, and we go on in like 12 minutes or something. Okay, so a small teaser exercise. Should be kind of trivial if you have like a function from A to B. Let's call it f, and eventually I have something like I don't know, A cross D, and I want to go to B cross D, and I tell you, okay, go the obvious way. Can somebody imagine which way am I imagining? I should, yes? Okay, so this function here, exactly, would be some that will consult f on this part, and here it will leave d the way it is, right? So it would be something like h of little a, little d. If I want to give it a name h, this would be equal to, help me here, f of a, d. I hope thinking of Manolis, I hope this makes sense. If I tell you consider the obvious function here, consulting f, it is this one. There's no way you will understand any other one. Okay. So the challenge is if we can translate this in a bit like more complicated ways. Like imagine you have a function. So here is something like given. Oops, sorry. You are given function like on the left, you have a function from C to C prime, and you are wondering if you have the same right, the same obviousness to say, okay, consider the obvious function from this thing to that thing. Can you always do that? And is there a way that you can check or something like that? If you don't know this, I think it's like hard to figure it out immediately. But if you start playing around, and you look here, I'm not complicating things too much because I'm avoiding sigma and p, but I do have products, I have arrows, I have sums, okay? So I don't want to give the answer here, but at least I would like to discuss any questions we may have as to what this homework asks. Yes, Ardi? There is a chance that you don't have the right to say consider the obvious thing. Here, in this silly example, I think you have the right to say consider the obvious thing. You have a function from A to B. You want to go from A cross D to B cross D. I mean, Lazarus gave this answer, but I think that any Lazarus who understands what's going on would only give this answer. So in a sense, I have the right to not even define it. I can say consider the function from here to there based on this f. Because there is only one that behaves properly. Okay. This takes some like some settings so that we can say it in a rigorous way. And you guessed it, we will have to do this starting from next week, that we will elaborate the promised vocabulary of category theory. So far, it's like investigating, and we can do it. When we shed some more categorical light, we will understand better what's going on. But I think we can still get to some satisfactory answer if we start playing around with some examples that are not suddenly so complicated. I mean, try to build this up. Try to see what happens if you have a sum here, if you have an arrow, and if you combine this. And then you probably will figure out a very important concept. An important concept here in this class means a concept that has interpretations in all three points of the triangle. Okay, so type theoretic, proof theoretic, and category theoretic. Okay, algebraic or algebra, logic, computation. It will manifest itself in all these. I would like, just some votes to see intuition. Who thinks I can always do that? Notice it's not. I mean, sorry. The big types are equal. It's the same thing, right? And I'm just inserting a prime somewhere, here, 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 and here. Okay. The second one I want to do actually two things. It's the same function here and here. Like go down, doing this function. So just checking intuition. Who thinks I can always do it? Okay. Who thinks I might be able to do it? Okay. Okay, and who thinks I can actually have a trick or like a way to figure it out that doesn't depend on which these types are? Because, for example, if you know that C prime here is, I don't know, the natural numbers, you can even ignore this one and say, okay, I will use here the function that's, I don't know, it will always be 42 here. Or maybe if you know all these types, you have a way to produce an element here, but obviously this is not what we want, okay? So, okay, enough for this thing. I will let you guys think about it. We'll come back to it when we have like a bit more vocabulary and find a very simple answer to this question. But you're right, the answer is not, we cannot always do it, and there is some trick I can see. If you know or if you spotted the trick, is it a question or an answer?
A question.
Okay, ask away.
What is the blue arrow?
The blue arrow is because this thing is a type, right? And the question is if I can, and this is another type, and the question is if I can somehow from this arrow that gets me from C to C prime, I can say, consider the obvious arrow that gets me from this type to that type.
So a function.
Yeah, it's a function. Yeah. It's a function from this big thing to that big thing that has to come in some way from this one. Exactly the way that your function got this thing and produced a function from this big thing to this big thing. Okay. Okay. So now, before we go to category theory, I want to establish some things about order theory, and it will not be all the order theory that we'll see in this course will not be like in the next 40 minutes. We'll come back to it and investigate further, but I want to start with some things. And my motivation here will be the entailment. This way we study two things at once. Remember when we were doing proof theory, I used this symbol called it entailment, and the idea is that I could have like hypothetical judgments. So these are, I consider them like my hypothesis. And here I have my conclusion. For example, A is true, and the idea is that this judgment, I call it hypothetical because it depends on these givens. If I write it like that, I am emphasizing the fact, or maybe even worse like that this does not depend on anything, that it doesn't have any open stuff. Okay, so I want to put this relation-looking thing on the table and see what kind of properties it should have, and maybe what kind of properties it does have, if it should deserve the name entailment, logical entailment. Okay, so first of all, I will start from the one that it's harder to doubt, which is like from A true, you should be able to infer, if you assume A true, you should be able to infer it from its own assumption, I mean from its own hypothesis. Anybody would like to attack this, like it doesn't make sense. For an entailment, the idea is from this, I can guarantee that. Obviously, if you give me A, I can guarantee A, I just give it back to you, right? So this should look like some kind of reflexivity. The next thing will end up being looking like this. If from A true, and I will add some context here, I can get, or maybe not from A true, okay, I'll do it like that. If from some hypothesis, I don't know, I will use gamma. I have been using gamma for some time now. I don't know if I mentioned anything about it. It's the standard letter we use to denote context, obviously because it's the third letter and gamma has some association with C. But we think of this like as a list here, right? It could be empty, 1, 2, or more than that, but it's like a list. So I have a bunch of assumptions there, or can be empty as well. So from this I can prove A, and further on, if from A I can prove B, can somebody guess what I should be able to conclude here? Yes, Rafael? Exactly. Rafael said from the same initial hypothesis here, gamma, I can conclude the other conclusion. This is exactly what, I mean, I don't know if you can spot it this like this. This is exactly a lemma. What we use lemmas in mathematics. You prove something, okay, and then you want to use it there, but you don't have to reprove it every time, but if somebody forced you to do it, you could just copy-paste the whole proof of the lemma inside your proof, and you could do it like that. Okay. So this is somehow related to transitivity. I hope you kind of see it, and this will become even clearer. Maybe this is kind of more than transitivity, but we'll come back to it. And I hope that this thing also makes sense, that an entailment relation should have this property. Questions? No. Then the following two properties, somebody could reasonably doubt. We will not do it here. We had this conversation a bit with Manolis. So the first one is called weakening, which says that if I prove from certain hypotheses A true, then I can definitely do this with some extra hypothesis H true. I can still get A true. And it's called weakening for obvious reasons, because this statement, if I have a proof of this is a stronger statement than that, right? Here, the truthness of the truth of A is guaranteed only from gamma, and here it has an extra hypothesis. It's a weaker statement. This is why it's called weakening. And the other one is called contraction. I will write it like that, and say that it doesn't make sense. Usually, as I said, it does make sense to doubt these ones that I'm writing right now, but we will not do it here. To ask for a hypothesis twice, because none of the rules we have will keep track of how many times you use something, even though there are logics that do that. Quite interesting ideas. And so from here I can get, okay, I'm not being consistent with my letters. I should have something like maybe H. Actually, no, A was right. It was okay here. A true. I will conclude my, B true here. So if I have this, I should be able to infer this. It doesn't really make sense to list. Doesn't make sense to ask how many times does, Euclid's lemma hold for this proof. And this will be contraction. And there's a final one that I will not bother to write it in full detail. I will say it orally. It's like, if from gamma you can get A true, and if you can permute the things in gamma, and that's a big if, then this also becomes true. In the setting I am, this if you can permute things does not make sense. It will make sense once we realize that context, I will write it right down. When I write this context here, let's say I have a vector inside this space and another vector in the same space maybe. I don't know, and I have another natural number, and then I have some matrix, I don't know, T, in this space. I don't know what I'm writing there, but let's say I have this context and I want to prove something. This should make sense for anybody who studied mathematics. You could have something starting like that. Let n be a natural number, u and v are vectors in R to the n, M is a natural number as well, and T is a matrix of this dimension there. I mean, this makes total sense mathematically as a statement. Then you will go proceed and prove something. My point here is I should be able, the order that these things appear doesn't matter as long as there are no dependencies. But we have dependencies here, so it doesn't make sense, for example, to swap these two. So it will be quite tedious to write this down. I'm just saying this orally. The idea is that this is something like permutation. You can permute things in gamma as long as you don't break dependencies. Okay. So anytime, I think I should mention this. Anytime you write a context, let's put like a pointer here on the first thing that I'm reading on the context. It should be the case that this thing is already a type. So when I'm reading this, I should know that n is a type out of what? Out of nowhere. I should know that already. The moment, and now I go on, like I move my pointer to the next. Now I'm reading this thing. And now what is implicit here? I should be able to have that this thing is type, but not now out of nowhere. I have the right to consult this thing. So here, it is implicit that I have this. And so on and so forth. And notice that, okay, I stepped on the second step, so this is not obvious. But the moment I go to the third step, on the third point, it can depend on the two previous things. And the third point, like this thing, depends on all those things, although it doesn't really depend in an essential way on those two, but it depends on an essential way on this and that. Okay, so I hope we understand what I mean with this permutation.
Sorry, you mean U at the bottom, right?
Probably. Where is that?
So from N to Rn, it should be U, the letter there, no?
This one here?
No.
Where?
Left, left.
Left? This one?
No.
Down? Yeah.
And one right.
Can everybody see it?
Next to, you say, prove N type, the last statement.
Okay, this one?
Yes, exactly, the first letter.
That's an N. And that's an, okay, so that's my bad handwriting. That's an N as well.
Yes, but the first one should be U, no?
This one?
Yes.
No. Because, okay, let me highlight this. This N here, like I need to have this natural number N in order for this thing to be a type. So it depends on this thing, which is exactly the previous variable that I have here. So it would be maybe like in a mathematical text, you wouldn't even mention that, right? You would say like, consider the Euclidean plane R to the N. Supposedly you are supposed to understand that let N be a natural number and stuff like that. Or maybe you see that in the other way around because you say something like let Rn be, I don't know, for some, and after that you say for some natural number n. But essentially the order is not that. The order is like each thing you introduce may depend on one or more of the previous things. It cannot depend on future things. Let's say like that. Okay. So let's see with this whole setup of the entailment. Let's move in an order theoretic approach. Let's put our order theoretic glasses and write. I will write this to mean here that A true can prove B true. And I want to see what kind of properties this relation has. I don't have the right to call it an order, obviously, because I haven't proved anything. But it's kind of indicative from the fact that I'm using this symbol that will end up being an order. So first of all, what is an order? And I will start with a pre-order, which is kind of more useful for me here. And I will confuse the two all the time. So sorry about that. It's on purpose. Pre-order is any relation that is reflexive and transitive. So let's see if it is. Reflexive means that I have this, and I do have this, because of we have accepted this thing, right? So this indeed is reflexivity now, and I need someone to help me to figure out transitivity, which is like that. A is less than B, and B is less or equal than C. Then A, we should not think of like usual order of real numbers or natural numbers as good examples of orders. Let's say that's a way to compare things, okay? That's all. And maybe some things are incomparable as well, which doesn't happen in the usual order of the natural number and the real numbers. So, if I translate this into what it means that A true, I will not write all this true here, from A true I get B true, and from B true I get C true. I should be able to conclude. Can somebody see how this happens? Manolis?
You use the above transitivity like King wrote.
It's a special case for this. Your only duty here is to tell me what is gamma, what is A, and what is B, so that it matches, right? So it's like this. Let me bring it down so that, sorry. Yeah, so I can see it now. Help me here.
So you have gamma is just a statement that A is true.
Exactly.
A above is B here.
So this is A true here as well. Let me do all substitutions. A true is A is B here, right?
Yeah. And
So B and B is C. Okay, so it's indeed a special case of these rules. Okay, so this relation that I'm defining in terms of this thing is reflexive and it is transitive, and it's not antisymmetric exactly, or maybe I don't know what antisymmetric means right now. Okay, I think you know this word, but I mean, okay, what is antisymmetric? Let me state this. It would be antisymmetric if I also had this. From A compares to B is less than B, and B is less than A, I can conclude that they are the same. Do I have this?
Obviously, no?
What?
Obviously.
Obviously I have this. Why? Let's see what this means. This means that if from A I can prove B, and if from B I can prove A, then they are the same.
Because this equal sign, I interpret it as the double proof symbol.
Okay. Okay, so then it's trivial. If you interpret like that, it's like pretty trivial, and you say, okay, I can consider equality here to mean this, but it's not really. I mean, if you think that you have a prior knowledge, or not knowledge, sorry, notion of equality, I mean, you look at let's say you look at A or A, and you look at A, okay, and it's true that these are interprovable, but like when you're forming these propositions, if I ask you, is it the same proposition?
No.
You would say no, right? But like 3 minutes ago, you would say obviously they are equal. So it's a different kind of equality if we are to consider them equal. And for the time being, I can develop the things I want without worrying too much about this. I can say I will not build things on top of partial orders. Partial orders, sorry, it's a pre-order together with this. Reflexive, transitive, and antisymmetric. So I could say maybe we will disagree in some kind of terminology because you say, every time I heard this word, it was a partial order, and say, okay, it doesn't matter that much. And it's an easy exercise to see to defend this thing. And I will, this is homework, defend this. Defend the name. Why is it called pre-order? So, in order to understand what this means, I will just tell you that when we say just order, it's implicit partial order, which is reflexive, transitive, and antisymmetric. So if you are to call something a pre-order, you should have a way to reach an order out of it. So that is like, it's something before it became an order. The construction is quite standard and usual that you usually do here in mathematics, but since order theory is not so studied, it's nice to see this in this setting as well. But as a kind of hint or spoiler, you have seen similar things like in group theory and ring theory and topological spaces or stuff like that. So it's this similar kind of trick you need to do. I will not worry about it right now. We will discuss this on Zulip. I want to say some interesting things that happen here because, from the proof theoretic and logic aspect, because I have this world, this order, has some very nice guarantees. It has what they are called meets. Has meets. I will say binary meets. And now you will ask me what is a meet. Binary meets. Given by, you'll tell me what they are given by. So, what is a meet? You know the idea of meet from probably calculus. It's a different word to say infimum, if you know this word, but I want to see it as a binary thing. I don't want to say the infimum of a huge set. I want to say, take these things and give me their meet, which will end up being, in our heart, meet means best, this is important, lower bound. So, first of all, what is a lower bound? So, the meet, which we denote like that, what a coincidence, must be a lower bound of A and B. So it has to be below them. So first of all, it's below A, and second of all, it's below B. You are probably thinking of conjunction, and this is like a good reason to avoid this symbol until this lecture. Unfortunately, I did not do it. Imagine we were using this symbol for conjunction until now, that we will realize that these things are related, and we say, okay, let's use the same symbol. So this is less than or B. And I have them without any further assumptions. So what I wrote here is that this weird, mysterious guy, don't look at this as a conjunction, look at it as some kind of construction I did using A and B. But it's some proposition, something in my space. And this thing is less than A, and this thing is less than B. It's below B. Okay? So far, I have said it's a lower bound. I want to say that it's the best lower bound. Usually you don't see the word best here, but you see which word? Greatest, okay? Which can be a synonym in English, but it's not used like a synonym. If you think of it as a greatest, please think of the greatest as in the sense of best and not in the sense of bigger. Because best in certain contexts means big and in other contexts means small, okay? So what does it mean? All the definitions we will see here will have the same format. First of all, they satisfy some things. Second of all, it's the best among all those things that satisfy these things. And we do that saying, consider as a candidate that also satisfies these things. My guy is better than your candidate. Okay, so this means that the best part will always be like this. Consider a candidate, I will use C for obvious reasons, that also is a lower bound. So far satisfies this part, and I want to say that this is enough to defend that my guy is better than this C. So what does this mean? Now I need to think. Best here, should my guy be less than or bigger? What is the correct notion of best in this sense? Can anyone defend one opinion or the other? Yes, Rafael.
Lower. Say lower of
Lower? So best means least.
No.
Okay, so you changed your mind because when I asked, you said greatest, right?
I
It was you. Oh, okay. Okay, so we disagree. We have a disagreement. And what was your?
Yeah, same.
The same list?
It's the smallest of all.
Okay. There is a silly metaphor, and I will use the silly metaphor to defend this. We are talking about lower bound, things that are both under something, right? Consider like you have a speed limit in your driving, and there's a speed limit of like, I don't know, 60, and you want to see all the drivers that did not get fined. Who is the best driver? Does that make sense? It's like if you drive above 60, you got fined, you are eliminated. But from the rest, the closer you get to the upper point, the better you are, let's say. The metaphor doesn't work so well if you consider like you are giving exams to enter the university and there is a cutting point, like I don't know what the base for mathematics department is, maybe, I don't know, it's like 14, I don't know, what is it nowadays? The base, I mean to, what? Yeah, the limiting point, like you have to, yeah. So let's say it's 15 out of 20, like, so who is the best student in this case? Among all those students that got inside, you want to say maybe the top mark, but no, because in essence, the person who got 15 is the most economical one. Made the least effort and is in the same place than everybody else. Let's say like that. This metaphor doesn't work as well because we associate higher marks with better things. But let's say we take this approach, the least thing. What is the least thing here? The thing out of which I can prove anything. Because remember, the least, this means from the left I can prove the right. So do I have a least element in this world? And what is this element? I'm looking for something out of which I can prove anything. We have met this proposition, yes? Yes, it's the bottom, the boom, right? Okay, so if you say that the best lower bound is the least one, for any A and B you will pick, the best guy will always be bottom. Always, one of the approaches, take the biggest or take the smallest, is meaningful and is the correct one, and the other one is like trivial. It's not interesting. Okay. Here, in fact, it is the greatest one, and so I need to say that my guy is bigger than this candidate. And anything that satisfies these things is called meet of A and B. Other names for meet are GLB, for greatest lower bound. I don't want to use this because I would like to call it BLB, and nobody calls it like that. I'm the only person that uses this notation. Also, it's called an infimum, a meet, and I think any other synonyms I'm forgetting? Yeah, probably not. Okay, so I'm saying that this relation has binary meets given by, and I've pretty much given the answer, and the notation is giving the answer by conjunction. Okay, so in this world of propositions, if you compare them with this order and pick any propositions you like, there is a certain one that deserves the name the meet of these things, which is the greatest lower bound, which is one that can prove, from which you can prove either of them, and from any other that can also serve to prove both of them, yours is better. Okay, this is the whole idea. Yes.
Μπορείς να αναλάβεις μία το conjunction λίγο, γιατί νομίζω ότι υπάρχει αμφισημία λίγο.
Yeah, thank you. Fancy word. Is it better now? Yeah, because we have been using this symbol and this symbol for conjunction so far. Okay, pretend that all conjunctions were like that, and now I'm saying that it has meets, and this thing that we already know satisfies these properties. So it is the meet there. Okay, it also has a bottom element, which Lazarus already spotted, has meets and a bottom. which is the bottom, okay? So again, Raphael will complain, the bottom is meaningless. It's not, because like I'm using bottom here in the order theoretic sense. So first of all, I have to tell you what bottom means. It means that it's, as you can imagine, it's less than any A, okay? And this ends up being the bottom as well. Again, maybe I should have used a different symbol for the logic part. Similarly, this thing has binary joins. What is a join? It's from, if you look all the upper bounds, the best one. So it's the best upper bounds. And probably you guessed it. Now it will be the other way around. So, and can somebody guess what the joins will end up being in this world? Yes? The disjunction, okay. Given by disjunction. Okay. So what are the properties I need? I need that this disjunction must be an upper bound. So things are flipped here. So far I'm saying that my guy is an upper bound. And it has to be better than any other candidate, so the same thing. Give me any other upper bound, I can guarantee that my guy, who is this guy, is better than your guy. Okay, so what better means here? So it will be the other way around, right? If I get the greatest thing, I will end up with top, always. It will be the lowest thing, so I need my guy to be lower than your guy. So we are investigating like a new concept for many of you, like an order theoretic concept of this join and meet. And I can give you tons of examples to convince you that you have seen exactly these things, maybe with bad definitions. I tend to criticize this, like shedding this order theoretic light, you will see them again in like good definitions. A good example of an order in a very known setting is if you take like the integers, but not with the usual order, but the order that is of real interest to the integers, which is the divides.
Divisibility.
Yes, this one, divisibility. Thank you. So first of all, is it reflexive? Do I have for any integer a that a divides a? Yes, I do. Is it transitive? From these things, can I conclude this? Is it antisymmetric?
Άμα το περιορίσουμε στο
If we restrict it to?
στο natural.
Don't consider the natural as a subset of the integers, please. If we restrict it like to greater than or equal to 0, okay, yes. I don't want to do that, and that's okay because I do not insist on antisymmetry. Okay, but if you look at like the integers from the point of view of divisibility, from the eyes of divisibility, you cannot see the difference between 3 and -3. Like you see that we draw things. It's about time I start drawing things. When we start the orders, we draw things. So we have something like that. And also 3 goes like to 6 because 3 divides 6, but 6 does not go back to 3. Okay, we tend to draw things. These are called Hasse diagrams, and we tend to draw them growing upwards. Like if I write this, the idea is that I have the right to tell you I gave you an order, and you understand all the relations from my drawing. And the idea is that I can conclude that that A is less or equal to B because there is a line that goes like going upwards to B. But I can also conclude that A is less than or equal to D, even though I am not drawing this line, and I should not draw this line, because since it's an order, and I'm telling you it's an order, you know that it's transitive, so from the fact that there is a path going upwards from A to B, you know that A is less than or equal to D. I think I said B. And how about C and D? They are incomparable, okay? So we always draw these diagrams. if we have a partial order, I don't even need arrows. If I'm on a pre-order, I maybe need the arrows because I have situations like this. But as a hint, like on how to solve the previous exercise, this homework of defend the name prayer, like if you zoom out a lot, I cannot zoom out that much. If you zoom out a lot, this will become like a dot, essentially. This is a hint of how to proceed to define an order out of a pre-order. But okay, let's go back to the integers. Okay, so it's an order. Do I have meets here? First of all, I need to translate these things in this language. So what would a meet be in this world of integers? Okay, first of all, it should be a lower bound. But what does lower mean? Every time I use terminology of order, it's mentally prefixed by a specific order that I have in mind. When you are a kid and you say like 3 is less than 5, you mean that 3 is this relation less than 5. Now, I'm considering a different relation, so I can say like this less than 5. My way of comparing integers now is not the usual order, it's this divides. So if I say it's a lower bound, it doesn't mean that it's less within traditional sense than both integer. It means what? Help me, somebody. Yes, Sotiris?
It divides it.
It divides both. Yes, so if it's a lower bound of A and B, it means, first of all, let's call it D. It divides A, and it also divides B. And also, it is the best. So how would we call it so far? We would call it like it's a common divisor, or it's a lower bound. I'm specifying that the way of comparing things is divisibility. Okay, so it's a lower bound. So it's a common divisor, and I want to say that it's the best common divisor. Yeah, but it's. I mean, maybe you say I've heard this phrase in my high school or in university. I want actually to see that this is what's going on here, because we are very wrongfully trained when we hear the word greatest divisor to think that it's the max of the divisors.
So largest.
Yeah, it's the largest thing, the maximum. With which order max? Usually we think that it's with this order, but this order is completely foreign here. Nobody cares about this order. When you're doing divisibility and number theory, you don't care about this order. The order that you care about is this. So if you see, for example, the common divisors, I don't want to pick a big example, but let's say of 6, I don't know, 6, and give me another example. So the divisors of 6, let's say, okay, you have 1, 2, 3, and 6. Am I missing anything? I think not. Okay, and then you have like the divisors of 9, which are like this. No, you should correct me. Okay, these are the common divisors. I will write a com div of, these are the divisors of 6. And these are the divisors of 9. And when you want to say the common divisors, it's the union of these things. No, sorry, the common divisor, the intersection, right? But the intersection is these guys here. Am I right? I think. And if you think that the greatest common divisor is like the max, you are completely mistaken in the sense that this max you are saying here is of a different order than the order we're using to compare things. It's not 3, because minus 3 and 3 have exactly the same rights as to I deserve the name greatest common divisor, because greatest means greatest. Okay? And minus 3 divides both 6 and 9, so it's a common divisor. And any divisor you pick, my divisor, minus 3, divides your divisor as well. So indeed, we have 2 greatest common divisors. And somebody can make some weird arbitrary choice and say, okay, I will show some prejudice against the negative numbers for some reason. I even call them negative, that's bad. And I will select 3 to be this thing. But if you go through all the proofs that you do, essentially you never use that it's the max of these things. They go through if you just say, give me a greatest common divisor, and I will only use these properties that the greatest common divisor has, which are exactly these two. So this is a familiar concept, meets, and I will let you think where they show up again. I mean, if you study sets, you will have some certain type of meets there, and similar things. Since the time is running up, I want to say something very interesting here, because so far I think in 1 second you will accept that I also have a top member in my world of the way, in this order I'm talking about, which will be the absolute truth proposition. But I do have something else. Okay, I think something very interesting here that is missing from this interpretation is this thing. And I think it's a nice exercise to try to characterize this, the implication, or the theoretically. And I'm looking at same kind of thing, a similar kind of thing. It has these properties, and it's the best thing that has these properties. And this is called an exponential, and we are approaching a structure. The first structure that we are approaching here is called a hating algebra, where we have joints and meets and tops and bottoms, and we have this comfort as well to take exponentials. Okay, I'm not sure if the next lecture will be to continue this, because I thought I would be able to finish this off today, or if we'll pause and see categorical things. We'll figure this out together. Exercise before you reach home, so that you will post it on Zulip. Try to figure out if there is a top and if there is a bottom in the world of integers through the eyes of divisibility, and try to design draw the integers, and ask yourselves who is in the zero floor, who is in the first floor, is there a last floor, is there a penultimate floor, stuff like that. Okay, so we stop here and we go on Zulip.